We keep saying we'll just move to Mars like it's some kind of cosmic backup plan. But have you ever actually stopped and asked whether a human being can really live there at all? In this video, we're going to look at what Mars actually offers you and follow that all the way to a harsh, uncomfortable answer. If you think the red planet is our escape route, stay with this, because by the end, the idea of just living on Mars is going to feel very different. Mars is often sold as our next home, but the first hard problem hits before rockets, cities, or terraforming. The planet basically has no usable air for you. At sea level on Earth, the air pushes on your body with around 100,000 pascals of pressure. That is one standard atmosphere, the environment every cell in your body expects. On Mars, right down on the surface, the pressure is around 600 pascals, less than 1% of that. That is roughly like being 30 kilometers up in Earth's sky, around 100,000 feet. No jet, no human operates naked at that altitude. In that kind of low pressure, your lungs cannot pull in enough molecules to support normal breathing. The gas is just too thin. Your blood is kept in check by your own internal pressure, so it does not suddenly boil, but exposed fluids like saliva can start to form bubbles and evaporate. Your eyes dry out, your chest feels like it is collapsing, you lose consciousness in seconds, and death follows very quickly after. There is no hold your breath and sprint back inside option, because it is not just about oxygen, it is the total pressure crushing down to almost nothing. So on Mars, stepping outside without a pressure suit is not brave, it is simply fatal. You need a full suit that holds a mini-Earth atmosphere tightly around your body, keeps that pressure constant, and stops your internal fluids from reacting to the near vacuum outside. The suit is not a convenience or a comfort, it is a life support shell. And it has to work perfectly every second you're outside. A bad seal, a cracked connector, a torn glove, and the environment rushes in to equalize pressure, which basically means the air rushes out of you. You might then say, all right, the outside is brutal, so we just stay indoors. We build good habitats, we pump Mars air inside, compress it to something reasonable, and live there. That sounds simple till you ask a very basic question. What is that Martian air actually made of? On Earth, about 21% of the atmosphere is oxygen, the gas your body burns with sugars and fats to make energy. Most of the rest is nitrogen, which is mostly inert in your lungs. On Mars, around 95% of the air is carbon dioxide. Oxygen is around 0.1%, effectively zero for human breathing. If you filled a room to Earth-like pressure using raw Mars air, you would not have a safe space. You would have a chamber full of a gas your body cannot use, with only trace amounts of what you actually need. And the problem is not just no oxygen. Carbon dioxide itself is a toxin at higher levels. Your brain is tuned to its concentration very tightly. On Earth, a small increase above normal makes you feel stuffy and uncomfortable. You breathe faster, your heart rate changes. At just a few percent carbon dioxide, you can get headaches, confusion, and panic. By around 10%, you can lose consciousness in minutes. Mars takes that dangerous gas and makes it the main ingredient of the atmosphere. So, to make air you can breathe, you do not merely compress what is outside and pump it indoors. You have to strip out almost all of the carbon dioxide, store or dump it, and either import oxygen from Earth or manufacture it on site by running energy-hungry machines that split molecules. That means constant heavy industry just to keep your habitat full of safe air. If those systems slow down, if they break, or if the power drops, the air quality inside starts to drift away from the narrow window where humans stay healthy. This leads to the next problem you might ask. If the atmosphere is mostly carbon dioxide, can we at least use it, together with water, to grow plants easily? Or tap liquid water on the surface to help with that? That sounds logical, but on Mars, even liquid water itself does not behave the way you expect. Because the surface pressure is so low, it sits close to the condition where water has trouble staying liquid. At those pressures, if you put down a puddle of liquid water at normal temperatures, say between 0 and 20 degrees Celsius, 32 to 68 degrees Fahrenheit, the water is not stable. It will quickly freeze into ice, or it will start boiling away into vapor, even though the temperature is not high. The physics there pushes water to choose solid or gas, not liquid, especially out in the open. This means you do not get natural lakes, streams, or rain cycles you can rely on. When people say Mars has water, they're technically right, but most of that water is locked up as ice, buried in the ground, or mixed with dust and salts. To get usable water, you're talking about mining frozen soil, heating it up from very low temperatures, melting the ice, then filtering out contaminants. That is a chain of energy-hungry steps, done over and over every single day, just to supply what on Earth comes out of a tap. So, your lake on Mars is not a place you stroll to with a bucket. It is a production system. There are drills, heaters, pumps, filters, tanks, all tied into your power grid. If any of those fail, your water supply drops. And because open liquid water outside is so unstable, you keep it inside pipes, storage tanks, or pressurized rooms, never really free, never really part of a natural cycle. Then there is the part that feels almost unfair. Even if you say, fine, we will not use the raw Martian atmosphere at all. We will generate our own mix of gases at the right pressure inside sealed habitats. Surely then we are safe, right? The answer is you are safer, but still right on the edge. Your lungs, sinuses, and the tiny blood vessels in your chest and head were all built by evolution under Earth conditions, with a certain pressure, a certain mix of oxygen, nitrogen, and trace gases. In a Mars habitat, you're asking your body to trust machinery to hold that narrow band exactly. A slight overbuild of carbon dioxide scrubbers, a stuck valve, a miscalibrated sensor, and the balance can shift without you noticing at first. You might feel tired, get a headache, feel weirdly anxious, and by the time you realize it is the air, levels might already be in a dangerous zone. On Earth, if a building's air system fails, you can open a door or window and let the outside fix it for you. On Mars, there is no open the window option because the outside air will kill you even faster. The planet does not provide a safe default environment. The default is a thin, toxic, low-pressure gas that your body cannot use directly, plus a surface that does not support standing liquid water. The only reason you're alive is because your machines are actively fighting that reality. Every breath you take on Mars depends on compressors, filters, pumps, sensors, and control software, all working correctly, all with backup parts, all maintained by people who are themselves depending on that same system. If the atmosphere is that unforgiving, if water is that hard to access, and if there is no natural backup anywhere outside your walls, then the question becomes very sharp. What happens when you put this fragile life support bubble into a world that is also extremely cold, where temperatures and pressure swings hit your equipment every single day? You already saw that Mars basically gives you no usable air. Now add one more layer. The planet is also cold on a level your body and your hardware are simply not built for. And that cold never lets up. Mars on average sits around -60 degrees Celsius, about -76 degrees Fahrenheit, as a kind of normal temperature. That is not a bad winter's night. That is deep freezer territory, planet-wide. At the poles, during night and winter, it can drop below -120 degrees Celsius, roughly -184 degrees Fahrenheit. That is colder than most lab freezers that store biological samples, colder than conditions where rubber stays flexible and standard lubricants behave correctly. So, before you think about cities, understand this: you are trying to run human life and delicate machines on a world that is naturally set to industrial refrigeration. You might think, fine, we will just insulate everything, we know how to deal with cold. But Earth's coldest places are short-term and local. Mars is long-term and global. Any exposed metal, seals, cables or joints are sitting in that deep cold for years. And they do not just sit there. They are constantly cycling as the temperature rises in the day and crashes again at night. Materials expand when they get warmer and contract when they cool down. And they all do it by slightly different amounts. That means every sol, every Martian day, your structures breathe in and out, tiny mechanical stresses building up, micro cracks forming in places you cannot see. Now, here is the next question. What happens if you go to the nice parts of Mars near the equator where it is supposed to be more friendly? In full sunlight, on a good day, the temperature at the equator can creep up to around plus 20 degrees Celsius, about 68 degrees Fahrenheit. That sounds almost comfortable, but by dawn, the same spot can plunge to around minus 70 degrees Celsius, roughly minus 94 degrees Fahrenheit. That is a swing of around 90 degrees Celsius, about 160 degrees Fahrenheit, in less than 24 hours. And this does not happen once. It happens every sol, again and again. On Earth, if you flew from a hot desert to the middle of Antarctica, you would feel that shock and your body would clearly know something extreme has changed. On Mars, your habitat walls, your pipes, your vehicles, and your spacesuits have to handle that kind of jump all the time, in place, with no break. The seals around airlocks, the windows on pressure modules, the joints on your rover, they're all expanding and contracting on a daily cycle. Over months and years, that is a recipe for wear, fatigue, and finally failure. Unless you over-engineer every single component with wide safety margins, extra mass, and constant inspection. Then you might say, all right, the temperature swings are bad, but at least the atmosphere is thin, so maybe it does not steal heat that fast. Maybe it feels like being high on a mountain. That sounds reasonable, but it is wrong in a dangerous way. On Mars, the air is too thin for normal convection to be your main heat loss. Instead, two other processes dominate: radiation into the black sky and conduction into the frozen ground. Your habitat, your suits, your vehicles, all of them are sitting on a very cold surface, under a very cold sky. And they are constantly losing heat through infrared radiation and direct contact with the ground. So your suit is not only trying to keep air in, it's also trying to keep heat in, against a universe that is effectively at just a few degrees above absolute zero. The regolith under your boots, the dusty rock, is a huge thermal sink, pulling warmth out of anything that touches it. The result is simple. The power you need just for heating is huge. If you want to keep a habitat at a comfortable 20 degrees Celsius in an environment sitting at minus 60 or colder and leaking heat in all directions, you're running heaters non-stop, you're burning electrical energy just to maintain room temperature. And if your power drops, the inside temperature starts tracking the outside much faster than you would like. Think about what that means during a power emergency. On Earth, if you lose power in a house in winter, the temperature drops slowly, maybe over many hours. You can put on a coat, call for help, go somewhere else. On Mars, if you lose power and you lose active heating, the cold outside is so extreme and your connection to it is so direct that your habitat can start falling towards unlivable temperatures in a much shorter time window. The same is true for pipes carrying water, waste, or air. They can freeze solid and burst. Then you're dealing with both a mechanical failure and a life support leak at the same time. Now add one more layer that is unique to Mars, something you never deal with on Earth at this scale. In winter, especially near the poles, the carbon dioxide in the atmosphere actually freezes out and falls as frost or snow. The air itself, the main gas in the atmosphere, turns into solid ice on the surface. When that happens, the total mass of gas in the atmosphere drops. The pressure changes. Then, in spring, the carbon dioxide warms back up, sublimates, and re-enters the atmosphere. So every Martian year, the planet is literally breathing in and out in terms of air pressure. For you, trying to build or even build anything serious on Mars, this is not just a neat fact, it is a problem. When carbon dioxide frost builds up on the surface and then disappears again, it can move dust, crack ground, and shift loads. You get frost heave, where the soil slightly lifts and settles as ice forms and melts. Except here, it is not just water ice, it is also frozen carbon dioxide. Any structures built in higher latitudes have to sit on foundations that can handle this slow seasonal flexing. If you build pipelines or cables across ground that moves, you risk stress points where things eventually snap. There is also the pressure side of this. When part of the atmosphere collapses into ice each winter and returns in spring, the global air pressure changes by a noticeable amount. Your outside vacuum is not even fully stable. It is swinging with the seasons. That means your habitats and suits, all built for a certain pressure difference between inside and outside, see slight changes in loading over the year. The systems that read outside pressure and control valves, airlocks and emergency vents have to handle that variation without drifting into dangerous settings. So, put all of this together. The baseline state of Mars is a deep freezer. The daily pattern is violent temperature swings. The heat loss channels are harsh and unforgiving, and the atmosphere itself freezes and unfreezes on a schedule that flexes your environment. You're not setting up a town in a cold place. You're fighting the planet's basic thermal behavior every hour just to stay in a narrow human comfort band. And remember, you're doing all of this on top of the earlier problem. The air outside is almost useless to you. Water does not sit in nice lakes, and every breath depends on a chain of machines that cannot fail. Now add one more question. Even if your technology can hold the right pressure, the right temperature, and the right chemistry, what happens to a human body that lives for years in a gravity field that is only 38% of what it was built for, with bones, muscles, and organs tuned for 1G, being forced to operate forever at 0.38G? You'd think weaker gravity would make life easier, less strain on your joints. Cool moon jump videos all day, right? On Mars, that lower gravity feels like a perk at first, but over years it quietly pulls your body apart in ways we do not really know how to fix. On Earth, you live at about 1G. The pull from our planet sets your weight, shapes your bones, and even helps guide how your organs sit inside you. Mars only gives you around 38% of that, roughly 0.38G. In numbers, Earth pulls you down at about 9.8 meters per second squared, Mars at around 3.7. That means if you weigh 70 kilograms on Earth, your mass is the same on Mars, but your weight feels closer to 26 kilograms, about 57 pounds. Sounds fun until you ask what happens to bones and muscles that never ever get their full normal load again. We already know what happens in microgravity in orbit around Earth. Astronauts who float for months lose around 1 to 2% of their bone mass per month if they do not follow strict exercise programs. Their muscles shrink, especially in the legs and core. Their spines lengthen a bit, which sounds cool until you realize it also means back pain and disc issues. That is in 0G. On Mars, you are not floating, but you're also not at 1G. You're in a constant in-between state where your skeleton is underloaded every second of your life. The real problem is nobody knows what decades at 0.38G actually do to a human spine, to hips, to knees, to all the cartilage that normally takes full Earth weight. Maybe bone loss slows, but never stops. Maybe joints remodel in weird ways. Maybe vertebrae compress differently. Maybe your discs degenerate faster. You're asking millions of years of evolution, tuned to 1G, to suddenly accept a new baseline. And the current plan is basically, we'll find out when we get there. That is not a safe design principle when you cannot evacuate people easily and medical infrastructure is minimal. Now look at your blood and your heart. On Earth, gravity pulls fluids downward, so your body builds a pressure gradient from your head to your feet. Your heart, your blood vessels, even the valves in your veins grew around that pattern. In 0 like on the International Space Station, fluids shift toward the head. Astronauts get puffy faces, skinny legs, stuffy noses, and over time, the shape and function of the heart can change. Some astronauts come back with vision problems because pressure in the head and around the eyes is different for months. Mars puts you into a regime nobody has really tested long-term. Not full weight, not weightless, fluids will still drift upward more than on Earth, but not as much as in orbit. That means strange blood pressure profiles your body has never seen before. Maybe your ankles never really feel heavy. Maybe your head is always a bit congested. Maybe your heart muscle slowly reshapes to push against a new, weaker gradient. You could end up with chronic swelling in some tissues, long-term changes in how your heart beats, and a whole new set of cardiovascular diseases that simply do not exist on Earth. Your entire circulation system is built for a roughly 1.8-meter tall fluid column for an average adult in one gyne. Mars rewrites that geometry and the force behind it permanently. Any medical guidelines, any risk charts we built on Earth are suddenly guesses because the baseline physics has changed. Then comes the really hard question. Not just can an adult survive on Mars, but what happens if you try to raise children there? Experiments with mice, fish, and other animals in partial gravity and rotating systems already show developmental issues when gravity is not normal. Bones form differently. Muscles do not bulk up the same way. The inner ear, which controls balance, can wire itself in a way that only makes sense for that specific gravity level. So, picture a child born and raised entirely at 0.38 guys. Their bones, muscles, tendons, and nervous system will treat that weaker gravity as normal. Their spine will grow under lower load. Their hip joints will never learn to carry Earth weight. Their heart and blood vessels will tune to a smaller pressure gradient. Bring that person back to 1G and Earth could feel like a crushing field. Every step like walking with a permanent heavy backpack. It is very possible their skeleton and organs simply could not cope, at least not without massive medical help if at all. In that scenario, a multi-planet species might quietly turn into multiple versions of humans that cannot live in each other's gravity wells. Martian-born people might be effectively locked to Mars, not just by distance and cost, but by biology. That is not the science fiction dream of a flexible roaming civilization. That is a set of separate, gravity-bound human branches. You might respond with the simple fix: we will just work out more. We will do heavy exercise. We know exercise helps astronauts. Yes, exercise helps, but Mars gravity also sets a hard cap on how much load you can put through your body using normal methods. That 70-kilogram person who weighed around 154 pounds on Earth now weighs the equivalent of about 57 pounds on Mars. If they do squats with only their body weight, their bones only see that lower load. To get Earth-level stress, you have to add a lot of extra weight or use machines that push harder than the gravity does. On Earth, you get resistance for free just by standing up. On Mars, you have to engineer it back in. That means exoskeleton suits that pull you downward or resist your movement, treadmill harnesses that hold you to the belt with strong springs or cables, resistance machines that push your joints to forces they never feel just walking around. To really match Earth conditions, you probably need centrifuge gyms, rotating rooms, or devices that spin you to simulate higher while you run or lift. All of that means more mass, more power, more maintenance, and more potential failure modes just to keep your skeleton from slowly dissolving. And remember, if you push too hard with artificial loads in a body that has already lost bone density or changed joint structures, you can cause fractures, tendon tears, or spine injuries. So, the training program has to walk a tight line, hard enough to fight bone loss, soft enough not to break people, all inside a sealed habitat on a planet where emergency surgery and rehab options are limited. So, add this up. Living on Mars means your bones are underloaded. Your heart and blood vessels are working in a weird in-between state, and your children might adapt so strongly to 0.38 degree that they can never safely visit the world their grandparents came from. You're not just building a base, you're accepting that your body will be in a permanent, uncontrolled experiment. And all of this is happening while you are already fighting thin, toxic air, extreme cold, and fragile life support systems. Now layer one more threat on top. Something you cannot see, cannot feel directly, but that hits every cell of your body every hour you spend there. The radiation that on Mars comes almost straight through the sky and down to your front door. On Earth, you live under a shield so strong you almost never think about it. On Mars, that shield is mostly gone and space is basically sitting on the surface with you. Earth has two big protectors, a thick atmosphere and a strong magnetic field. They block and deflect a lot of high-energy particles from the Sun and from the rest of the galaxy. Mars has almost no global magnetic field and only a thin layer of air. So, the stuff we call space radiation does not really start above the sky there. It comes right down to ground level, to your habitat walls, to your suit and to your body. Start with the steady background, the galactic cosmic rays. These are high-energy particles flying in from outside the solar system, and they are pretty much always there. Measurements from the Curiosity rover show that on the Martian surface you get around 0.2 to 0.7 millisieverts of radiation per day. In a year on Earth, a typical person might get about 3 millisieverts from natural background sources. So, in just 5 to 15 days on Mars, you already take the same dose you would spread over an entire year on Earth. Stay there for a full Martian year, and you are looking at something like 25 to 80 times the yearly dose you're used to on this planet. And that is before you include any big solar outbursts. What does that actually mean for your body? Radiation at these levels does not usually knock you down on the spot, but it does chip away at your DNA. It causes breaks, small chemical changes, and damage that your cells have to repair constantly. Your body can fix a lot, but not perfectly. So over time, the mistakes add up. The long-term results are higher cancer risk, potential damage to bone marrow, possible effects on the heart and blood vessels, and at higher levels, impacts on the nervous system. On Earth, the atmosphere and magnetic field flatten a lot of that risk. On Mars, you're taking a much more direct hit, and that is just the baseline, the quiet day. The real spikes come from the Sun, when it decides to throw a tantrum. Solar particle events, big flares, and coronal mass ejections can launch swarms of energetic protons and other particles across space. When those hit Earth, our magnetic field and thick atmosphere absorb most of it. You might get some radio disruption, some auroras, maybe a small increase in radiation on planes. On Mars, without that strong shield, those particles can punch through the thin air and slam into the surface much more effectively. For you, sitting in a lightly shielded habitat or out in a spacesuit, a strong solar storm is not just a pretty aurora event. It can be a serious medical threat. In a matter of hours, you could absorb a dose similar to a full-body CT scan, or, in extreme cases, something well beyond that. At those levels, you're talking about nausea, fatigue, possible genetic damage, radiation sickness, and another big chunk of lifetime cancer risk in a single event. If your emergency shelter is not designed with enough shielding, or if you cannot reach it in time from wherever you're working, Mars does not give you a second chance. You cannot just ride it out in a thin-walled habitat and hope it is fine. So you might say, all right, we take this seriously, we will build proper shielding. But then the physics hits your logistics. To really cut down radiation from above, you want mass, a lot of it between you and the sky. Water is good, thick plastic is decent. Rock and Martian soil, the regolith, also work. You are looking at tens of centimeters of solid material as a minimum, and more like 1 to 3 meters, about 3 to 10 feet of soil over your head if you want strong protection against both cosmic rays and solar events. Now think about what that means for a real base. Say you have a habitat with 100 square meters of floor area, around 1,000 square feet, a small house. Cover that with 2 meters of regolith with a typical soil density, and you're already talking about hundreds of tons of material piled on top. Push it to 3 meters and you're easily in the range of many hundreds of tons. That is not something you casually lift with a small rover. You either dig into the ground, making tunnels and caves, or you build strong structures and then bury them under huge amounts of Martian dirt. That already kills the fantasy of big glass domes and open plazas under the sky. Transparent materials are usually bad at blocking high-energy particles. You cannot just sit under a wide window and call it safe. A realistic settlement looks more like a buried bunker or an underground base with maybe small, heavily shielded windows or short-term viewing areas. When you go outside for work, you limit the time. You track everyone's accumulated dose, and you treat unshielded exposure as a serious controlled risk, not a casual stroll. Even with all that, the total dose over a Mars mission is brutal compared to Earth standards. A round-trip flight, months in deep space each way, plus a stay of a year or two on the surface, can easily push an astronaut's cumulative dose into the range of 600 to 1,000 millisieverts. That is enough to hit or exceed many current career limits for astronauts. It means a clearly increased chance of developing cancer later in life and possibly other long-term health effects we do not fully understand yet, especially for the brain. Now, extend that from a 2 or 3 year mission to a 20-year life on Mars. You're talking about a population living under a constant slow sandblasting of their DNA, with occasional big hits from solar events if anything goes wrong with shielding or scheduling. Children, pregnant people, older adults, anyone with a medical condition, they all stack dose year after year with no easy path to return to Earth. No quick medical escape to a low radiation environment. This is not the same as living at high altitude on Earth, where radiation is a bit higher but still low in absolute terms. Mars shifts the entire baseline up. You can reduce it with mass, with careful design, with underground structures, but you cannot bring it back down to Earth levels unless you are willing to basically live inside a heavily shielded shell almost all the time. And every kilogram of shielding has to be mined, moved, and installed with equipment that itself is taking radiation damage. So, put this in context. On Mars, your air is thin and toxic. Your gravity is slowly pushing your skeleton and heart into unknown territory. And your environment is bathing you in radiation that Earth's shield normally absorbs for you. You are living in a bunker under meters of dirt, tracking your dose like a bank account, knowing that every extravehicular activity, every trip outside, is another withdrawal. And while all of that is hitting your cells and your materials from above, another threat is waiting literally under your boots, the planet's own dust, ground down to microscopic shards that want to get into your lungs, into your machines, and into every gap in your life support systems. You can build thick walls. You can bury habitats under meters of soil. But there's one enemy on Mars that keeps getting through anyway: the dust. And this is not just dirt you wipe off with a cloth. This stuff goes after your lungs, your machines, and your food supply at the same time. Martian dust is extremely fine. Many particles are only a few micrometers across, about the size of the particles in cigarette smoke. At that size, they don't just stop in your nose or throat. They go deep into the smallest branches of your lungs, into regions where your body clears material very slowly, if at all. On the Moon, Apollo astronauts reported lunar hay fever, after breathing in just a little bit of lunar dust that leaked into the lander. That was from a few days of exposure. On Mars, you are talking about months and years in habitats that are constantly at risk of minor leaks and tract contamination. And the Martian atmosphere, even though it's thin, is enough to keep this dust in motion. It doesn't fall out quickly like heavier sand on Earth. It hangs. It gets picked up by winds. It gets into cracks. It stays suspended longer. Every time you open an airlock, every time you cycle people in and out, some fraction of that dust will try to ride along. Filters catch a lot of it, but no filter is perfect forever, and you are living right next to the source. The chemistry makes it worse. Rovers and landers have found perchlorate salts in Martian soil, roughly 0.5% to 1% by weight. Perchlorates interfere with the thyroid gland, which controls metabolism, growth, and energy balance in your body. Even at relatively low concentrations, long-term exposure is not something you want. If that dust gets into your air, into your water, or into your food production systems, you're not just dealing with harmless mineral powder, you're dealing with a slow chemical insult to your hormones and possibly your entire health. So, when people talk about using Martian soil to grow food, the first reality check is that you cannot just put seeds into that dirt and add water. You have to process tons of soil, not kilograms, tons. You wash it, you chemically treat it, you flush out perchlorates and other salts, you test it, and only then do you start thinking about plants. That is a lot of water, a lot of energy, and a lot of equipment, all just to get something close to the kind of soil you get almost free on Earth. Now look at the physical side. On Earth, many sand grains are rounded off by water, wind, and time. On Mars, there is no liquid water smoothing out the edges, and the dust particles tend to be sharp and jagged at the microscopic level. That makes them abrasive. They scrape and grind on seals, on moving parts, on joints in spacesuits, on rover wheels, on solar panel surfaces. Over thousands of cycles, that abrasion wears things out, makes small grooves, opens up paths for leaks. The low humidity and constant friction also mean the dust gets electrically charged very easily. It sticks to surfaces, including your suit, your tools, your visors. In the same annoying way, fine powder sticks to plastic, except here it is not just messy, it is dangerous. After a single trip outside, your suit is coated. When you come back in, unless your airlock system is extremely good at cleaning it off, some of that dust comes in with you. Airlocks turn into dust concentrators unless you design them to act like full decontamination chambers with air jets, vacuums, maybe even sticky or rotating surfaces. All of it consuming more power and adding more complexity. Inside the habitat, all of your protection now comes down to filtration, duct design, and maintenance. You are breathing at your filter's performance. If the filters are new, well-seated, and rated for particles in the few micron range, fine. As they load up with dust, as seals age, as someone installs one slightly wrong during a rushed maintenance cycle, efficiency drops. A small leak in the system doesn't just mean a dusty room. It means chronic inhalation of particles your lungs struggle to clear, loaded with perchlorates and other reactive compounds. Long-term, that points to higher risks of chronic lung disease, inflammation, and possibly cancer. It also means increased strain on your immune system, which, remember, is already dealing with radiation exposure, altered gravity, and stress. Every spacewalk, every external repair, every construction job becomes a negotiation with the dust. You want to get people outside to build and fix things, but bringing them back in means a new round of contamination risks each time. The machines are in the same fight. Dust in bearings, dust in gears, dust in electrical connectors, dust on radiators that are supposed to dump heat into space. Coatings that looked fine in testing on Earth might erode faster than expected. Seals that passed thousands of cycles in a clean lab might fail early when abrasive dust is ground into them day after day. Solar panels lose efficiency as dust accumulates, which means less power, which means less margin for heating, filtration, and every other life support function. You can design cleaning systems, robotic brushes, gas blowers, maybe even electrostatic repellents, but all of that is one more subsystem you have to build, power, and keep working. So, the surface of Mars is not just a cold, quiet desert. It is an active source of tiny, sharp, chemically nasty particles that want to enter your lungs and your machines. You cannot pave the entire planet. You cannot keep dust out completely. You can only manage how fast it gets in and how well you clean it up. And here is the part that links straight into the next threat. The dust is not just sitting there waiting for you to step on it. The atmosphere, thin as it is constantly moving it around the planet, lifting it into the sky. Sometimes a few meters up, sometimes tens of kilometers up, turning whole regions, and sometimes the entire globe, into a dim reddish haze that blocks sunlight and attacks your power supply right when you need it most. You've already got air that wants to kill you, gravity that slowly pulls your body apart, and radiation pouring through the sky. Now add a planet where the weather is set up to go after your power supply and your visibility at the same time. On Mars, you don't just deal with a bit of dust now and then. Dust storms can start as small whirlwinds, local events, then link together and grow until they wrap around the entire planet. In some years, you get global dust storms that last for weeks. When that happens, sunlight at the surface can drop by 90% or more. At Mars's distance from the Sun, the incoming energy at the top of the atmosphere is already only around 590 watts per square meter, less than half of Earth's. Cut that by 90% with dust, and at the surface you're down to a weak, coppery twilight all day. That has a very simple consequence. Your solar panels stop being your main power source. A farm of panels that looked good on paper suddenly produces a small fraction of its usual output. On Earth, a cloudy day might cut power, but you still get a decent amount. On Mars, during a global dust storm, the drop is much more severe and lasts much longer. That's why "we'll just go off-grid with solar" is basically a fantasy there. If you rely mainly on sunlight, you must have deep energy storage and realistically some kind of nuclear backup, or your life support and heating are running on borrowed time. You might think if the storms are that dramatic, then the winds must be brutal, tearing apart structures like hurricanes. But Mars tricks you here. Typical peak winds in big storms can hit around 30 meters per second, roughly 110 kilometers per hour, or about 70 miles per hour, which sounds like a strong storm on Earth. But the air is only about 1% as dense as Earth's, so the force on large surfaces is far smaller. These winds don't usually knock down big buildings or flip heavy rovers. Instead, the real effect is more subtle and more dangerous long-term. The winds are just strong enough and the air is just dense enough to pick up and keep those fine dust particles suspended. The planet's thin atmosphere becomes a delivery system, lifting dust off the ground, carrying it across continents, and dropping it onto everything you care about. The power of the wind is not in pushing you over, it's in scraping your equipment and blocking your sky. Now think about your hardware. Your radiators, your solar panels, your thermal control systems were all designed with certain assumptions about how well they can get rid of heat or collect light. When dust settles on radiators that were supposed to radiate heat away into space, their surface properties change. They start to act more like insulation. Electronics that were meant to stay within a safe temperature range now run hotter right when you also have less power to actively cool them. At the same time, the dust on your solar panels cuts their efficiency. So, your power generation collapses just when your thermal management load goes up. That means you don't just design solar panels, you design a full dust management ecosystem around them. You need mechanical brushes, gas blowers, maybe electrostatic or sonic systems to shake or repel dust off critical surfaces. All of that must work in low pressure, low temperature, and must keep working for years while itself being attacked by the same dust it's trying to fight. Every extra cleaning system takes more power and more maintenance, which you already don't have much margin for during a storm. Visibility is another problem you cannot ignore. During the worst global storms, the sky can become so thick with dust that the horizon almost disappears. Cameras on landers and rovers see only a dim orange fog. For a human crew, that translates to seriously limited navigation. Driving rovers becomes risky, landing new hardware becomes harder, and even simple outdoor tasks can turn dangerous because you lose depth perception and landmarks. If you can't see rocks, slopes, or the edge of a crater clearly, one mistake with a vehicle can end in a rollover or a stuck rover far from safety. So, during a major storm, your crew might be forced to stay indoors for weeks. Extravehicular activities get pushed to emergencies only. Construction halts. Repairs that require outside work are delayed. Meanwhile, dust keeps settling on everything and your power budget shrinks. You end up rationing energy, heat versus air, recycling versus water processing versus communications. On Earth, bad weather is an inconvenience. On Mars, it can pause your entire surface civilization. And storms don't need to be global to cause trouble. Regional and local storms can still cut solar input a lot, still load your air filters with dust, still sandblast exposed materials. They also inject fresh dust into the atmosphere that later settles as a thin layer over your base. So, even in normal years with no planet-wide events, you're constantly cleaning, constantly monitoring filters, constantly watching power output curves for signs that panels are getting choked again. There's also the landing issue. Any long-term presence on Mars depends on sending more cargo and eventually more people. But landing through dust-thick skies is harder. Your radar and optical sensors have to see the ground accurately. Your engines have to deal with blowing dust on final descent, and your landing site has to stay safe as the surface changes. A bad storm during a crucial landing window adds one more layer of risk to an already complex operation. So, put all of this together. The weather on Mars, with its dust storms and long periods of dim light, doesn't just make things a bit harder, it directly attacks your main power source. It overheats your electronics, it blinds your navigation, and it slows or stops surface work right when your systems need more attention, not less. You're trying to run a high-tech outpost in a place where the sky periodically turns down the dimmer switch on your entire energy system. And remember what comes next in the chain. While the storms are cutting power and loading everything with dust, you still need water every day for drinking, for air recycling, for growing food, and for making fuel. On Mars, that water isn't sitting in lakes or rivers. It's locked in ice and frozen soil that you have to dig up and melt with the very energy the storms are choking off. People say Mars has water, like that solves the problem. But the part they skip is how hard it is to turn that water from a map label into something you can actually drink, breathe, or grow food with. Most of the accessible water on Mars is locked up as ice, and a lot of that ice is in the wrong places for easy human landings. High latitudes, closer to the poles, have clearer, shallower deposits. But those regions are colder, darker for long parts of the year, and harder to supply with power. The nice landing zones you keep seeing in concept art, the lower latitude, relatively flat areas, usually have water buried under dry regolith tens of centimeters to meters down, mixed with dust and salts. So you're not drilling a well into a liquid aquifer. You're running a mining operation for frozen salty mud, not for the metal, but just for water. Every kilogram of that dirt you haul up contains some fraction of ice, and you have to go through the whole chain every day because your crew, your life support, and your crops never stop needing water. Now look at the energy side of this. Say the ice in the ground is sitting at around -80 degrees Celsius, about -112 degrees Fahrenheit. To turn that into usable liquid water, you first have to heat it up to 0 degrees, then you have to actually melt it and then keep it above freezing while you clean it. That's a large temperature jump. When you do the math, you're spending hundreds of kilojoules of energy for every single liter of water, depending on the starting temperature and how dirty it is. 1 liter might not sound like much, but a small outpost with a handful of people, plus some plants and basic industry, can easily need hundreds or thousands of liters per day. Drinking, washing, oxygen production, food growth, industrial processes, all of it adds up. Multiply those hundreds of kilojoules by 1,000 liters, and now you're locking a huge chunk of your daily power budget into just moving water from frozen dirt to clean liquid you can use. And that's before you factor in the machines themselves. The drills, heaters, pumps, and processors all have their own inefficiencies and losses. Nothing is perfect. Some heat leaks away into the surrounding ground, some gets radiated into space, some is wasted in mechanical friction. On Earth, water systems often rely on gravity and natural pressure differences. On Mars, everything is forced. You push every step of the process with electricity or reactor power. Then there's the water cycle problem. On Earth, you have rain, rivers, groundwater, lakes, and oceans feeding into clouds and back again. If you spill clean water on the ground or steam escapes into the air, it's still part of the overall cycle. On Mars, the surface and atmosphere basically run on a thin sublimation cycle. Ice turns directly into vapor. Vapor can condense as thin frost, and over longer timescales, some of that vapor simply leaks away to space because the gravity and the thin atmosphere can't hold all of it forever. So, when you lose water on Mars, it's not just a local plumbing issue, it's often a permanent loss. Venting moist air, dumping wastewater outside without recovery, or letting leaks go unfixed doesn't just raise your utility bill, it slowly shrinks your total water inventory. There is no ocean-sized backup, no fast natural recharge. Your colony's water is more like a bank account, with a slow, weak income stream and a lot of ways to overspend. Every kilogram you waste is one you might never get back. Even when you finally get your ice melted, the chemistry hits you again. Martian ice and the surrounding soil can carry perchlorates and other salts. That means you can't assume melted equals safe. You need full water treatment all the time. Filtration to remove particles, chemical processes to break down or remove perchlorates, probably multiple stages of purification for drinking water, and different standards for industrial water versus human use. So now, in addition to mining and melting, you're also running what is basically a continuous water treatment plant. Pumps, filters, reaction tanks, sensors, storage tanks, control software, all of it must run without major contamination or failure. Filters clog and need replacement. Resins and catalysts wear out. Tanks need periodic cleaning. Sensors drift and have to be recalibrated. Every step consumes parts and power, and every maintenance job exposes your system to the risk of mistakes. Think about what happens during an interruption. If your power output falls because a dust storm cuts your solar input, your heaters and pumps might have to throttle down. If you reduce water production, you start rationing. Maybe you cut back on washing and some industrial uses first, but eventually that squeezes life support margins too. If a treatment stage fails, you face a different choice. Use partially treated water and take health risks, or halt usage and scramble to fix the system before tanks run low. And remember, you can't just ship in more water easily. Every kilogram of water you send from Earth costs a lot in launch energy and money. Long-term, shipping water is not a realistic way to sustain a settlement. You are locked into making local extraction and recycling work under harsh conditions, with equipment that is constantly stressed by cold, dust, and radiation. Recycling helps, but even the best closed-loop systems leak a bit. You lose some water in vented air, in leaks, in irreversible chemical reactions, in accidents. On Earth, that loss disappears into a massive, forgiving environment. On Mars, you track every kilogram. Over years, those leaks add up, and you're forced to mine more ice just to stay level. So, when people say Mars has water, it is technically true, but operationally misleading. The planet gives you frozen, salty, chemically complicated ice in awkward locations and asks you to spend a huge amount of energy and hardware just to turn it into something that would come out of a cheap tap on Earth. Now stack that on top of everything else. You need high, constant power to mine ice, to heat it, to purify it, and to recycle it. At the same time, the sun is dimmer, dust storms are cutting your solar panels, nights are brutally cold, and batteries hate those conditions. The next question is obvious. How do you keep all of this running when the entire planet is, from a power point of view, a place that starts with a low energy budget and then keeps trying to drain it even further? How do you run a high-tech human outpost in a place where the whole planet is basically on low battery by default? On Mars, that is the core problem. Before fancy cities or terraforming, you are already losing the energy game. Start with the sun, because that is the first number that hurts you. At Earth's orbit, the sunlight at the top of the atmosphere is about 1,360 watts per square meter. At Mars, because it is farther from the sun, that drops to around 590 watts per square meter, a bit over 40% of Earth's value. That is just the raw sunlight before you lose anything to dust in the air, before panel efficiency, before the angle of the surface, before shadows from your own buildings. So, if you had a solar farm on Earth that comfortably runs a modest base, the same level of technology on Mars suddenly gives you less than half the power for the same area. To match it, you have to build more than twice the area of panels at minimum, spread over a harsh, dusty landscape. Then you add reality. Dust settling on the panels, storms dimming the sky, lower temperatures affecting performance, and you find that even a huge solar farm still collapses in output during dust season. The numbers say it bluntly. Solar alone will not save you, not if you intend to stay for years and grow. Now, think about energy storage. On Earth, batteries already have a hard time in winter. On Mars, nighttime temperatures easily drop below -80 degrees Celsius, around -112 degrees Fahrenheit, as a routine thing. Many nights are worse. Batteries hate that kind of cold. Their internal chemistry slows down, capacity drops, and internal resistance goes up. And if you keep cycling them in that state, their lifespan shrinks fast. So you face two options, both bad. You either burn precious power just to keep the batteries warm inside insulated boxes, or you accept that they will perform poorly and die sooner, forcing you to bring or manufacture replacements more often. Every kilowatt-hour you store is a fight against cold and inefficiency. The energy you put into batteries during the day has to cover life support, heating, water processing, communications, and also the power needed to keep the storage itself alive through the night. If you underestimate that, your system ends up in a downward spiral, where you keep spending more energy on protecting the infrastructure that was supposed to give you energy in the first place. This is why people jump to nuclear power when they talk about Mars. A compact reactor that runs day and night, unaffected by dust storms, looks like the obvious answer. A few megawatts of steady output suddenly make life a lot easier. Heaters stay on, mining rigs keep working, water plants run continuously, habitats sit at stable temperature. On paper, it fixes many problems in one shot, but reactors do not grow on Mars. Every reactor, every kilogram of fuel, every control rod, every spare part has to be built on Earth and then shipped across roughly 225 million kilometers, about 140 million miles of space at opposition. The mass is huge, the engineering is complex, and you do not get many chances to launch. Once a reactor is on Mars, you must keep it running safely with severely limited hardware support, under radiation, dust and cold, for years. If that reactor fails badly or has to be shut down, your off-world civilization can drop from a powered base to something closer to a cold, dark camp very quickly. Swapping in a new reactor is not like rolling up a diesel generator in a fuel truck. It means waiting for the next launch window, building and qualifying a new unit, and sending it on a months-long trip. You're betting your entire energy infrastructure on a small number of very complex machines with long gaps between resupply opportunities. So maybe you think, fine, we'll back it up with old-school generators the way we do on Earth when the grid fails. But Mars does not give you that option. There is no oil to drill, no coal seams, no natural gas fields. Fossil fuels are not just missing as a resource, they are missing as a concept. On Earth, a remote station can wheel in a diesel generator and a tank and have a huge amount of flexible backup energy on demand. On Mars, there is nothing like that waiting underground. You can manufacture fuel, for example, by making methane and oxygen using carbon dioxide from the air and hydrogen from water through something like the Sabatier process. But notice what that implies. Before you get 1 kilogram of methane, you had to collect water, which we already saw is expensive to extract and clean. You had to break that water into hydrogen and oxygen using electricity, and you had to run reactors to combine gases under controlled conditions. That means you spent a lot of electrical energy and water up front to produce a fuel that, when burned, only gives you part of that energy back. So, any backup generator running on locally made methane is not free security. It is just another way of converting your already scarce power into a different form. If your electrical grid is struggling, your water production is marginal, and your reactors are under pressure, you're not going to casually divert huge chunks of that capacity just to make emergency fuel. Mars gives you nothing for free in the energy department. Every joule is paid for with infrastructure, complexity, and risk. Put all of this together, you're on a world that starts with 40-odd% of Earth's sunlight, then covers that sunlight with dust, throws long, freezing nights at your batteries, forces you to ship any serious reactors across interplanetary space, and offers you no quick, dense chemical fuels as backup. Your water extraction systems, your air processors, your heating, your radiation shielding, your mining rigs, your transport vehicles, all sit on top of this fragile power foundation. When that foundation wobbles, everything else follows. A long dust storm hits, solar power drops, batteries run colder and weaker, heaters have to be throttled, ice mining slows, water production falls, air recycling margins shrink. The whole life support chain starts tightening, link by link. You do not just lose comfort, you risk crossing into conditions where one more failure pushes you into a real emergency. And that leads straight into the most unforgiving part of the whole picture. On Mars, you're not just using power to run lights and tools. You're using it to actively replace the natural systems that do everything for free on Earth. Your air, your water, your food, your waste handling, all of it depends on machines running every hour, with no real backup from the outside environment. So the next question is simple and brutal. What does it really mean to live your entire life inside a closed life support loop on a planet where a single broken pump or contaminated reactor can start a countdown no one can easily stop? You don't really live on Mars, you live inside a machine. And that machine has to work every second without a break for as long as you stay alive there. On Earth, air and water are just there. The planet runs the life support system for you, using oceans, forests, soil, and weather. You breathe out carbon dioxide, plants absorb it, they release oxygen, rain cleans the air, rivers carry waste downstream, and the atmosphere buffers small mistakes. On Mars, none of that exists. The cycles that keep you alive are not planetary, they are mechanical. Pumps move air, filters scrub carbon dioxide, reactors split molecules, bioreactors grow algae or plants to recycle waste. If one important valve sticks, if a sensor fails low or fails high, if a control loop is coded wrong, you can go from a normal day to a life support incident in hours. Think about air first. Your habitat has to keep oxygen in a narrow range. It has to keep carbon dioxide below a limit. It has to manage humidity and trace gases. One software update that misreads a sensor, one pump that slows down, one scrubber cartridge that saturates earlier than expected, and levels begin to drift. You do not see the problem until people start getting headaches, feeling dizzy, or alarms finally trip. By then, you're already in active response mode. There is no outside breeze you can let in to reset everything. The air outside is thin, cold, and full of carbon dioxide. Your only fix is to repair the system that is failing while breathing the air that depends on it. Water is the same story. Every drop in your tanks has been mined, melted, and cleaned with real effort. That water is circulating through drinking taps, hygiene systems, hydroponics, radiators, and industrial loops. If a filter clogs and ruptures, if a tank grows the wrong microbes, if a chemical dosing pump fails and overdoses or underdoses a treatment stage, you can quickly contaminate a large fraction of your stored water. On Earth, a bad batch can be dumped or diluted. On Mars, dumping means throwing away days of mining and melting work and shrinking your total reserves. You don't waste water lightly when every kilogram came out of frozen ground with a big energy bill attached. Food adds another layer. If you're serious about living there, you cannot ship all your calories from Earth forever. You need greenhouses, algae tanks, or microbial reactors to recycle nutrients and grow new biomass. That means light, water, nutrients, controlled temperature, and a carefully balanced microbial community in soils or solutions. A single pathogen, a mold outbreak, a nutrient imbalance, or a failing lamp array can wipe out a crop cycle. On Earth, a bad harvest is painful but often local, and global agriculture covers the loss. On Mars, a failed harvest in your main greenhouse is a direct hit to your food security months down the line. Why not just bring massive redundancy for everything? Because the physics of getting mass to Mars is brutal. To push 1 kilogram from Earth's surface up to low orbit, you need around 9.4 kilometers per second of velocity change, delta V. To send it onward to Mars, you add several more kilometers per second with upper stages or transfer vehicles. In real terms, every extra kilogram of equipment, spare parts or emergency supplies costs a lot in launch capacity and money, and it has to be booked years in advance. So you cannot bring spares for everything. You pick and choose, extra pump or extra filter, more reactor components or more medical hardware, more radiation shielding bricks or more greenhouse equipment. Every kilogram is a trade-off, and once it is on Mars, you do not get a quick resupply if you guess wrong. The next launch window comes roughly every 26 months, and the ship you need has to be built, tested, and launched at exactly the right time. To escape this resupply trap, people talk about bioregenerative life support using plants, algae, and microbes to close the loops. That idea is promising, but right now it sits mostly at laboratory scale and in small test beds. We have not yet run a closed system with hundreds or thousands of people for decades, with all the messy realities of human life, waste, disease, and random failures. The International Space Station recycles water and scrubs air, but it still depends heavily on resupply from Earth. On Mars, you don't get that backing atmosphere outside the wall. If your internal ecosystem crashes, if the balance of gases, nutrients, and microbes in your bioreactors flips to a bad state, there is no planet-sized reservoir to lean on. Restarting that system is not like opening a window or venting a room. It might mean flushing tanks, regrowing cultures from frozen backups, replanting greenhouses, and living on emergency rations and bottled oxygen while you do it, all with limited spare parts and limited power. Maintenance in that environment is not a side job. It is the core of your civilization. Every pump, every valve, every sensor, every circuit board, every seal in an air duct, all of it has to be checked, cleaned, replaced, calibrated, and logged on a strict schedule. On Earth, you can get away with a broken fan for a while because the outside air can leak in and help. On Mars, a broken fan in the wrong subsystem means stale pockets of air, rising carbon dioxide, or dead zones in your greenhouse. So, instead of settlers in the classic sense, you have a team of operators running a planetary-scale industrial plant whose one product is survival. Everyone is part colonist, part mechanic, part emergency responder. Your day is divided between whatever your main specialty is and the shared labor of keeping life support, power, and water systems inside their tight limits. You are constantly watching trend plots, listening for odd noises from pumps, feeling for vibrations in ducts, double-checking software alarms. Fatigue and human error creep in. Someone skips a minor inspection because they are exhausted. Someone overrides an alarm just to stop the noise and forgets to reset it. Someone mislabels a replacement filter or tightens a fitting badly during a rushed repair. On Earth, a lot of those small mistakes wash out into a huge, forgiving environment. On Mars, they accumulate inside a closed system where there is very little slack. One overlooked crack in a pipe can slowly leak precious water into a wall. One miscalibrated gas sensor can underreport carbon dioxide until symptoms show up in people's bodies instead of on the screen. And this is just the mechanical side. The harder truth is that you are not alone in those loops. Your body, your gut, your skin, your lungs, they all carry trillions of microbes. The same is true for everyone on the crew. In a sealed, recycled environment, those microbes become part of the life support ecosystem. Whether you like it or not, they move through air filters, cling to surfaces, hitchhike in water, adapt to radiation and altered gravity, and evolve over time in ways you cannot fully predict. So, the next problem isn't just, can the machines keep running? It's what happens when human biology, human microbes, and Martian conditions all mix inside a closed system for years. Once you ask that, you realize you're not just exporting people to another planet, you're exporting entire ecosystems in fragile containers. And you have almost no experience with what that looks like after a decade. You think you're sending a few humans to Mars, but what you're really sending is billions of tiny passengers that evolved for Earth and have no idea how to behave anywhere else. Every person in that habitat is not just a body, they're a moving ecosystem. And that ecosystem reacts to Mars in ways we don't fully understand. Start with your microbiome. The community of bacteria, viruses, and fungi that live in your gut, on your skin, and in your airways. On Earth, they adapted to 1G, to normal Earth radiation levels, to diets based on fresh food, varied microbes in the environment, and constant exposure to new people and places. On Mars, you change all of that at once. Gravity drops to 0.38 G, radiation goes up, the diet shifts to packaged food, hydroponic crops, processed water. The air is recycled over and over. You touch the same surfaces, breathe the same filtered air, and live with the same small group of people every day. Your immune system is tuned to a certain pattern of contact with microbes. Change the pattern and it can overreact or underreact. Maybe some bacteria in your gut become more dominant when you eat more processed, shelf-stable food. Maybe others shrink because you don't get the same fibers or fresh inputs you had on Earth. That can affect digestion, mood, and even mental health because your microbiome talks to your nervous system through chemicals and the immune system. Add higher radiation, which can damage microbial DNA too, and you open up evolutionary paths we haven't mapped. Now think about pathogens in that closed loop. On Earth, a mild flu virus can spread through a city, but it eventually burns out as immunity builds and people separate. On Mars, you have a small crew in a sealed habitat, sharing air, water, and surfaces. If a virus gets in, it doesn't have millions of people to infect, but it also doesn't have anywhere to disappear to. It can keep cycling through the same group, hitting people again as their immunity wanes, or infecting new arrivals later. Radiation and stress make that worse. Higher radiation levels can increase mutation rates in DNA and RNA, including in viruses and bacteria. A pathogen that circulates for years in a small, stressed community under constant radiation is in an environment that pushes it to change. You could end up with variants that behave differently than anything seen on Earth, with unusual symptoms or resistance patterns. And you can't just wait for the season to pass. There is no new fresh air mass moving in from another continent, no summer festival of outside mixing that reshapes the disease landscape. It's the same few immune systems over and over. Planetary protection adds another dimension. Right now, space agencies put real effort into not contaminating Mars with Earth microbes. Probes are baked, cleaned, and handled carefully to reduce the number of hitchhikers. Humans blow that door wide open. We leak microbes all the time through breath, sweat, skin flakes, waste. Once you land people, you seed the local environment with Earth life, even if you try to be careful. And the reverse risk is not zero. If Mars has any native life at all, even just hardy microbes in certain soils or ice deposits, you're taking a big step when you introduce them into a warm, pressurized, nutrient-rich habitat. They might die quickly because they can't handle oxygen or our chemistry. Or they might adapt and grow because you just gave them conditions much better than the cold, dry surface outside. You could end up with new biofilms, weird corrosion, or interactions with your own microbes that nobody predicted. You are basically running a live biological experiment 24 hours a day with your crew and your habitat as the test bed. There is no timeout button, and the data you need, how mixed ecosystems of Earth and possible Martian life behave over decades, doesn't exist yet. You're learning while you're inside the Petri dish. Now, think about what happens when something goes medically wrong. On Earth, if a case looks complicated, you escalate. You move from a small clinic to a bigger hospital, then to a specialized center if you have to. You get access to advanced imaging, expert surgeons, big blood banks, and backup teams. On Mars, the biggest hospital is whatever you packed into a lander and bolted into the habitat. That's it. If someone needs complex surgery, say a major spinal procedure after an injury in low gravity, you have limited tools, limited blood, limited sterilization capacity, and maybe one doctor who trained in that area years ago. If someone develops cancer, you might have basic diagnostic tools and a few treatment options, but not the full range of radiation therapy equipment or specialized drugs you'd get on Earth. For weird infections, especially those that might involve mutated microbes in your closed system, you can send data home, but even at the best alignment, signals take several minutes one way. You're never in real-time contact with experts. Every medical decision happens on hard mode. You don't have easy access to donor organs. You don't have a deep pool of people for clinical trials. You don't have ready flights to a bigger hospital. The person you're treating is someone your whole small community knows personally, and losing them hits both operational capacity and psychology at the same time. Even routine healthcare gets harder. Dentistry in low gravity, pregnancy and childbirth at 0.38 degrees, long-term management of chronic diseases like diabetes or heart conditions in a place with different fluid dynamics and higher radiation. None of that has a tested playbook. You can extrapolate from Earth data, but you're guessing in crucial places, and when you guess wrong, you can't send the patient home. There is no back to Earth tomorrow. The transfer windows are about every 26 months, and the trip itself takes months. So layer this together. Your microbiome is shifting under new conditions. Pathogens are trapped with you in a feedback loop. You might be mixing unknown Martian chemistry with Earth life in ways nobody can fully model. And your medical system is a small, isolated setup with little room for error. You're not just changing your address from one planet to another, you're changing the entire biological context your body expects, with no real escape route if it goes bad. And all of this is happening while you live in confined modules under constant risk, cut off from real-time conversation with anyone back home. Once you account for that, you have to face the next layer of difficulty, not in your cells or your machines, but in your mind. What happens to people when their whole world is a small, dangerous bubble on a silent red planet? And walking outside without a suit is the same thing as choosing to die. Even if every machine on Mars worked perfectly, your brain still has to live with what that actually feels like, day after day, year after year, and that's a completely different problem than fixing a pump or swapping a filter. Start with the distance in the most basic sense, talking to people back on Earth. The time delay between Earth and Mars is not a small glitch. It is built into the speed of light. At the closest alignment, signals take around 4 minutes one way, at the worst, more than 20 minutes one way. So, a simple back and forth, you ask a question, they answer, can easily chew up half an hour or more. You don't get real-time voice calls. You get something closer to very slow texting with long gaps. On Earth, if you have a bad day, you can call a friend, talk it out, hear them respond, feel that live connection. On Mars, call a friend turns into send a message and wait. And maybe by the time the reply comes, your mood has shifted, the crisis has moved on, or you don't even feel like talking anymore. That lag changes how support feels. You're not just far away physically, you're functionally disconnected in human terms. You can send videos, you can get advice, but you lose that instant sense that someone is right there with you in the moment. Now look at your physical world. Your whole environment is a small set of spaces. A habitat, maybe a few modules, some tunnels, a rover, and outside that, a surface that kills you in seconds without full gear. The outdoors is not a relaxing option, it is an operational zone. On Earth, you get constant, effortless sensory variety. Different weather, different skies, different crowds, different sounds. You walk through a park, stand by the ocean, sit in a busy street, all without thinking about it. On Mars, most of your sensory input is fixed. Same walls, same colors, same hum of fans and pumps, same filtered air, same small group of faces. Your brain uses variation as a stabilizer. It resets itself based on changing light, changing sounds, casual contact with strangers, random minor events. Take that away, compress everything into a few controlled modules, and monotony becomes a real stressor. Days blur, you mark time with checklists and mission logs. Even if you rotate tasks, you're still inside the same narrow box, under the same constant background threat that if anything major fails, you're in trouble. Then there's the social environment. Put a few dozen people together in a closed space under steady risk, under strict schedules, and you're not just doing engineering, you're running a social experiment. Hierarchies matter, leadership style matters. One person with a difficult personality doesn't just annoy you for a few hours and then disappear into a city. They're there every day at meals, meetings, in emergency drills. Arguments don't have space to diffuse. Grudges do not get diluted by a wider world. Group dynamics can lock into patterns that are hard to break. Stress amplifies all of that. People are working long hours on critical systems. Sleep gets disturbed by alarms, by noise, by worry. If someone starts burning out, there's no easy way to send them on vacation, no real weekend away. Small conflicts over chores, schedules, or priorities can grow into big tensions because there is nowhere to step away and cool off in a real sense. Depression, anxiety, and irritability are not edge cases. They are expected outcomes unless you invest a huge amount of effort in selection, training, mental health support, and clear governance. And remember, everyone knows exactly what is at stake all the time. When you walk through the habitat, you pass life support panels, radiation monitors, pressure gauges. You know consciously that a major failure in any of those could kill you and everyone you know on the planet. That constant background knowledge is different from abstract risks on Earth. Here, it is personal, immediate, right outside the hull. Then there's the hardest psychological trap, the lack of a real exit. On Earth, if a job is destroying you, you can quit. If a city feels suffocating, you can move. Even with money or visa limits, there are usually multiple escape routes. On Mars, "I'm done, I want out," is not an option you can act on quickly. The launch windows for going home open about every 26 months, and that's assuming a return vehicle is there, fueled and ready, and the program actually lets you leave. So, you are locked into the experiment emotionally and physically. If you discover you hate the environment, if the social group doesn't fit you, if the constant risk eats at you, your choices are limited. You keep going or you break. Knowing that you have no simple exit amplifies pressure. Problems that might be tolerable for a few months on Earth become much heavier when you realize they might stretch for years before you can even attempt to leave. Put this together and you get a very different picture than the heroic poster version. Life on Mars is a tight loop of familiar corridors, slow, delayed contact with home, a small social circle that never really goes away, and a constant awareness that the outside world is not your friend. You might be surrounded by advanced tech, but your subjective world can still feel narrow, repetitive, and tense. And that's before you add in grief, accidents, or long-term health issues. If someone dies in an incident, there is no large society to absorb that loss. It hits the whole group at once, and the systems still have to run, repairs still have to be done. There is no pause button on life support while people process what happened. So even if you solve the engineering, even if you nail the life support loops and power systems, you still have a set of humans stuck in a red, silent environment with limited freedom and delayed contact with the rest of the species. The next question is unavoidable. If that is what daily life feels like on Mars, how much worse does it get when you remember just how far away you really are? How long it takes to travel there and back? And how few chances you get to send help when something goes wrong. Distance is not just a number between two planets, it's a hard limit on how fast you can fix mistakes, rescue people, or change your mind. And Mars sits on the wrong side of that limit. Getting there in the first place is already a major mission. Even if you use an efficient transfer orbit, the kind of Hochman transfer people usually talk about, a one-way trip takes around 6 to 9 months. That's 6 to 9 months in a cramped vehicle in microgravity, with radiation levels higher than anything on the surface of Earth, with no immediate rescue option at all. If something goes seriously wrong in deep space, nobody is turning a ship around in time to help you. The best you get is advice sent by radio, minutes delayed, while you try to fix the problem with whatever tools and parts you already have on board. And remember, that trip is just the prologue. You go through months of risk just to arrive at the place where the hard part really starts, living on Mars for years. Any plan that talks casually about sending people to Mars has to own the fact that each of those people spends the better part of a year inside a metal tube with the same few faces, dealing with bone loss, muscle loss, radiation, and no exit before they even see the planet's surface. Then there's the timing. Earth and Mars don't sit still. They orbit the Sun at different speeds. They only line up in a way that makes energy-efficient transfers possible roughly every 2.1 Earth years, about every 26 months. That's your launch window. Miss it, and you wait for the next one. There is no "we'll launch next week instead" when you're talking about interplanetary transfer. The physics doesn't care about your schedule, your budget, or your crisis. It only cares about where the planets are in their orbits. That has brutal consequences for operations. On Earth, if a remote base runs low on supplies or hits a technical problem, you can ship cargo quickly by air or by sea in a few weeks. On Mars, if a key piece of equipment fails after the window has passed, emergency resupply is basically impossible. You can send a small, very fast probe with high energy and a tiny payload, but you're not sending tons of food, water filters, or reactor components on short notice. Fast evacuation is not a concept that exists for Mars. If you want to leave outside the launch window, you're looking at very high energy, extremely expensive trajectories that are not going to be available as routine. Underneath all of this is delta V, the total change in velocity you need to make a journey. To get off Earth and into space at all, you need to hit something like 11.2 kilometers per second just to escape the planet's gravity well. Then you need more delta V to shape your orbit, rendezvous with a transfer vehicle, and match orbits with Mars at the other end. Energetically, Mars is far, not just in distance, but in the sheer amount of energy per kilogram you have to spend to get anything there and then slow it down safely to the surface. In plain terms, sending stuff to Mars is very, very expensive in energy, hardware, and money. And that is not going to change quickly just because rockets get a bit cheaper. You still have to climb out of a deep gravity well, cross tens of millions of kilometers of space, and land on another world. Reusable rockets help, but they don't erase the basic physics. Every kilogram of payload to Mars represents a long chain of launches, fuel, staging, and careful planning. That is why, in a Mars mission, every single kilogram has to earn its place. On Earth, when you design a system, you can overspec things. You can add extra bracing, extra redundancy, extra comfort gear, because the penalty is mostly cost and maybe shipping volume. On Mars, every extra bolt, every extra chair, every comfort item competes directly with water, food, oxygen, medical supplies, spare parts, radiation shielding, and scientific equipment. You want thicker walls on a module, that's more mass to launch. You want more exercise equipment to fight bone loss, that's less room for other hardware unless you increase total mass again. You want more medical gear, more backup computers, more replacement pumps. Good, but something else has to move off the manifest or wait for a later mission. The logistics budget is not just about money, it's physics limited. Rockets can only push so much mass per launch, and launch windows only open at certain times. This constraint flows into every design decision. Do you bring a secondary recycler or more spare parts for the first one? Do you pack large, comfortable private cabins or use that mass for a larger storm shelter with better radiation shielding? Do you send more people for social stability and productivity or fewer people with more equipment per person? On Earth, you often solve problems by shipping more stuff later. On Mars, you have to solve many of those problems up front in the design because there is no guarantee that later arrives before something critical fails. Even building up infrastructure is slow. Suppose you want a serious base with multiple habitats, vehicles, reactors, and factories. You're not doing that in 1 or 2 launches. You're talking about a campaign of missions over a decade or more. Each one pushing out another batch of modules, machines, and supplies, each one limited by mass, timing, and risk. If one key cargo ship is lost on the way, you don't just lose hardware, you lose the exact pieces that the whole architecture was counting on. So Mars is not just another continent where you ship containers by sea and planes by air. It is a moving target across interplanetary space that only lines up with you at specific intervals, with a deep energy barrier in between. That barrier turns logistics into one of the main things shaping what is even possible. It squeezes margins, stretches timelines, and forces harsh choices long before a single human ever steps onto the surface. Now add this final twist. When people run into all these blocks, thin air, cold, gravity, radiation, dust, distance, the instinctive answer is, fine, we'll change the planet, we'll terraform Mars, we'll make it more like Earth. That sounds like a clever workaround until you look at the numbers and realize that on any human timescale, Mars doesn't bend. The idea of turning it into a backup Earth isn't just optimistic, it's basically a myth. Terraforming is the part of the Mars story where people usually relax and say, "It's fine, we'll just fix the planet." When you look at the actual numbers, that idea falls apart fast. Even fixing Mars is not really on the table for anything like a human timescale. Start with the favorite simple plan. Warm Mars up by dumping more carbon dioxide into the air. The logic goes, carbon dioxide is a greenhouse gas. Mars has carbon dioxide in its polar caps and in the regolith, so melt it, release it, thicken the air, trap more heat, and you're on your way. The problem is, there just isn't enough of it. Studies of Mars's poles and soil show that even if you somehow vaporized all the excess carbon dioxide in the ice caps and all the gas loosely trapped in the surface layers, you do not get anywhere close to Earth pressure. You get something like a few tens of millibars. For comparison, Earth at sea level sits around 1013 millibars. So you're still at a small fraction of 1 atmosphere, still in near vacuum territory. You don't get lakes and oceans. You don't get stable liquid water under an open sky. And you definitely don't get a situation where you stroll outside in a jacket and breathe without a mask. Walking outside without a suit stays in the science fiction column. And even if you somehow cheated and imported extra gases, dumping manufactured greenhouse gases or nitrogen from somewhere else in the solar system, Mars has another built-in problem. It cannot really hold on to thick atmospheres for free. The planet's magnetic field is weak and patchy. It doesn't wrap the whole world in a protective bubble the way Earth's field does. That means the solar wind, a stream of charged particles from the sun, can interact directly with the upper atmosphere and slowly strip gases away into space. We've actually seen this process in data from orbiters. Mars has lost atmosphere over billions of years and the mechanisms are still operating. So terraformers run into a basic issue. Even if you spend centuries releasing gases, you're doing it in a system that leaks. It's like trying to heat a house where the windows are cracked open all the time and the front door never really closes. You can pump more heat in, but you are fighting a constant drain. On human timescales, that means any thick atmosphere you manage to build has to be actively maintained. Stop the effort and the planet slowly slides back toward thin, cold air. Then there is the timescale problem. Engineering a whole planet is not the same as tweaking a local climate or restoring a forest. You're talking about changing the composition, pressure, and temperature of an entire world. Then stabilizing those changes against ongoing losses to space and internal feedbacks. Realistic models push that kind of work into thousands to millions of years of sustained effort. For reference, most human civilizations we talk about in history lasted a few hundred years at best. Modern industrial civilization, the one capable of even thinking about terraforming, has been around for maybe 1 or 2 centuries. So, when people say we'll terraform Mars, they are casually proposing a project that is 10 to 1,000 times longer than any system we've ever built and any continuous technological tradition we've ever maintained. You are betting that your descendants, through wars, collapses, cultural shifts, and technological changes, will keep feeding energy, resources, and attention into the same planetary scale project for a time span that, from our point of view, is almost geological. There is no evidence humans can maintain that kind of focus, and a lot of evidence that we don't. Because of that, the fantasy quietly shrinks. Instead of "we'll make Mars like Earth," it becomes "we'll build domes." You put up giant transparent structures, or you bury habitats under regolith, and you call that terraforming. But that is not changing the planet. That is building a chain of high-maintenance spacecraft glued down to the surface. Under a dome, you still need pressure walls, life support, water treatment, power, and radiation shielding. You still need to manage dust, leaks, and equipment failures. You've just increased the volume you have to maintain and given yourself more surface area for problems. The red desert outside is still as deadly as it was before. The air outside is still thin and toxic. The temperature swings, dust storms, and radiation are still there, waiting a few centimeters away from where you stand. A dome sounds like a simple fix, but it actually amplifies risk. A small habitat with thick walls is easier to shield and easier to monitor for leaks. A giant glass-like dome is harder to protect from impacts, harder to shield from radiation, and harder to repair if part of it fails. One structural crack in the wrong place, and you have a huge volume of pressurized air suddenly trying to escape into a near vacuum. That's not a gentle failure mode. And none of this changes the fundamental reality that Mars does not give you the free services Earth gives you. Even under domes, you're not breathing a regenerated, planet-scale atmosphere. You are breathing air pushed around by fans and scrubbed by machines. You're drinking water that came out of ice mining rigs and treatment plants. You're eating food grown in artificial soils or hydroponic trays. The basic conditions outside the walls remain hostile. You're not settled in the sense people mean when they talk about living on Earth. You're stationed, like being posted indefinitely on a remote, dangerous base. So, the honest picture is this: terraforming Mars into a true second Earth is beyond us for any time frame that matters to you, your children, or their children. The planet will not be turned into a blue-green world with open seas and breathable air, not in centuries, probably not in millennia. What we can do is build more or less sophisticated life support bubbles on top of or under a frozen, thin-aired, radiation-exposed desert. And even if you accept that, even if you say, fine, we'll live in those bubbles and treat Mars as a permanent outpost, there is more to worry about. The ground you're building on is not perfectly stable. Mars looks quiet, but it still shakes, it still shifts, and it still gets hit from space more often than Earth does. The next layer of problems isn't just above you in the sky, it's under your feet and falling out of the sky in the form of rocks you never see coming. Mars looks calm in photos, frozen, empty, harmless, but that's an illusion. The planet is still moving, still reshaping itself in slow, sharp ways that matter a lot when your whole survival depends on fragile structures sitting on that surface. Start with Marsquakes. The InSight lander has picked up quakes up to around magnitude 4. On Earth, that's not a big deal. Most people would barely notice. But Mars is not covered in thick soil, plants, and deep weathered rock the same way. A lot of the surface is rigid, brittle regolith and fractured rock. When it shakes, even modestly, you can get landslides along crater rims, cliff faces, and canyon walls. So, if you decide to build into a slope for radiation shielding or put infrastructure near steep features for convenience, a small Marsquake can still trigger mass movement that undermines foundations or buries hardware. You also have to remember your structures are pressurized shells. On Earth, if the ground shifts a bit under a house, maybe you get a crack in the wall, maybe a pipe breaks. It's annoying, but not instantly lethal. On Mars, a slip in the ground that twists a habitat ring or a tunnel entry can stress seals, open microfractures, and eventually cause leaks. The regolith doesn't absorb motion the way softer Earth soils do. So, more of that energy can end up in your supports and anchors. When you design foundations there, you're not just thinking about static load. You're thinking about what happens when the whole base gets a quick jolt through brittle ground. Now shift scale down and look at the constant small motions across the surface. The dust devils. These are little vortices, like tiny tornadoes, that race across the landscape, lifting dust and sand. Individually, they're not dramatic. They don't throw rovers into the air or tear off solar panels. But over years, over decades, thousands of passes add up. They scour paint and coatings, they sandblast exposed surfaces, they move grains into new drifts and hollows. That means anything you leave sitting outside is in a slow erosion test all the time. Dust devils also rework the very ground you're trying to treat as solid. Paths that were clear can get new ripples and small dunes. Shallow trenches can fill, Cables you thought were buried enough might get exposed in spots, then buried again, shifting as the regolith creeps around them. Landing pads gradually roughen as particles are lifted and dropped. You can't just survey a site once, build and assume it stays the same. The surface keeps changing in detail, and those details matter when you're landing rockets or driving wheeled vehicles with tight safety margins. Layered on top of that is the seasonal frost cycle. Mars doesn't just have water ice, it also has carbon dioxide that freezes out of the atmosphere at the poles in winter. Each year, carbon dioxide and water frost deposit and then sublimate again as seasons change. That means the amount of solid material at or near the surface changes cyclically, and with it, local pressure and ground stability can shift. Over time, this can destabilize slopes and undermine foundations bit by bit. Imagine building a long pipeline or a row of habitat modules on ground that year after year has ice forming in pores and then disappearing. In some areas, the regolith can puff up slightly when ice forms and settle when it vanishes, a process similar to frost heave on Earth, but now involving both water and carbon dioxide ice. Your structure might not collapse suddenly, but you could see slow tilting, differential settling, and strain on joints and connectors. Over 10 or 20 years, that's enough to push things out of spec, especially when combined with thermal expansion cycles and dust erosion. Now, look upward at what comes in from space. Earth's atmosphere is thick enough that most small meteoroids burn up as harmless shooting stars. Tons of space rock hit the atmosphere every day, and almost all of it vaporizes before reaching the ground. Mars doesn't have that protection. The atmosphere is too thin to generate the same level of friction and heating for small objects. That means more of those rocks make it all the way down as impacts. Most of these are small, not dinosaur killer events, but they still matter over time. A small impact that would have been a streak of light on Earth can become a real crater on Mars, throwing ejecta in all directions. If that happens near your base, you could get debris hitting habitats, solar farms, antennas, or vehicles. Even if nothing critical is hit directly, the shockwave through the ground can jar equipment, and ejecta can add yet another layer of dust over everything. Over decades, as you place more hardware across a wider area, the odds go up that something significant gets hit, or that an impact alters terrain in a way that your original maps no longer capture. You can't assume the surface is a static platform, it's more like a slow, random hazard generator. Tie all of this together and the picture becomes clear. Mars is not a friendly, frozen museum piece where you can set up delicate equipment and trust the ground. It has quakes that can shake brittle regolith, slopes that can give way, dust devils that slowly sand away your assets, frost cycles that quietly twist and lift your foundations, and a thin sky that lets more space rocks reach the surface than you're used to. So, what does that mean for long-term building? It means over-engineering everything. Deeper, stronger foundations, more flexible joints, redundant seals, regular surveys of the ground with radar and other sensors to spot changes before they turn into failures. It means spreading out critical systems so one impact or landslide doesn't take everything at once. It means budgeting for a level of inspection and maintenance that makes even harsh Earth environments look easy. And all this is on top of the hostile air, the cold, the radiation, the dust, the power problems, the biology issues, and the psychological pressure. You're spending enormous engineering effort just to stand still, just to keep a small population alive on a planet that does not want to host you. At that point, you have to ask a different kind of question. If the physics, geology, and logistics make life on Mars this fragile and this expensive, what does that do to the economics and the ethics of sending people there in the first place? Are you really living on Mars, or are you just surviving in an extreme, high-cost lab? And what does it mean to ask people and their children to sign up for that? By now, it's clear Mars is not welcoming you. So the next hard step is this: if surviving there is that hard, who pays for it? And what exactly are they buying when they send a human being to live in that environment? Start with raw cost, because physics turns into price very fast. Getting 1 kilogram from Earth's surface all the way to the Martian surface isn't cheap just because rockets get a bit reusable. By the time you stack launch, transfer, braking and landing, you're still talking about costs in the tens of thousands of dollars per kilogram, even with very optimistic assumptions. That's for anything: a wrench, a bag of food, a battery. Now, scale that up to one person plus everything that person needs to not die. A human is not just 70 or 80 kilograms of mass. Add their share of habitat volume, structure, life support, hardware, radiation shielding, food stocks, water, suits, tools, medical gear, and margin. You are quickly in the range of tens of tons per person, tens of thousands of kilograms. Multiply that by tens of thousands of dollars per kilogram, and each colonist represents a multi-billion-dollar logistics package just to get started, before they produce anything, before you factor in resupply, replacements, or emergencies. That alone flips the idea of a cheap frontier. On Earth, new towns can grow because the basic environment is free. You put up buildings, run pipes, and the air, the rain, the soil are already working for you. On Mars, every kilogram that makes life possible has to be bought, built, and thrown across space. The planet does not give you free infrastructure. You ship it, or you fabricate it from scratch with machines you also shipped. Then comes the part most people don't like to think about. You never stop paying the maintenance bill. Cities on Earth eventually become economically self-sustaining. They import and export goods, they repair roads with local asphalt, they build new hospitals with local industry, they mine materials from nearby regions. A Martian settlement has no such base at the beginning and may never fully get one. Every pump, every circuit board, every seal in an airlock has a lifetime. It will fail. High radiation, dust, and constant cycling will probably shorten that lifetime compared to Earth. When it fails, you either replace it with a spare you brought or you manufacture a new one on Mars. But manufacturing complex components locally means building factories, which themselves need machines, feedstock, power, and people to run them. You've just turned keep people alive into build and maintain a growing chain of industry in the harshest place you've ever tried to live. In practice, that means you're likely stuck in a hybrid mode for a long time. Some things you fix or print locally, many others still need to be shipped from Earth on a schedule tied to launch windows. A critical pump type, a specialized chip, a reactor part, a medical device, these are not easy to bootstrap from raw Martian rock. So the stream of cargo keeps flowing every 2-year window, each shipment carrying high-value items that the base needs simply to stay at the same level of capability. Miss a few cycles, have a major technical problem, or suffer an economic crisis on Earth, and that maintenance chain starts to break. The settlement doesn't coast along gracefully, it begins degrading. Some systems move from fully functional to barely functional. Redundancy gets eaten. Safety margins shrink. The idea that a Mars city will just stand on its own feet the way a terrestrial city does ignores that the planet itself is not providing any of the background support. The maintenance line never ends. Now bring ethics into this. You're not sending robots. You're sending people who feel pain, who form relationships, who have children. You're asking them to live in a place where failure modes are brutally unforgiving. One major system collapse, power, air, water, radiation shielding, can mean mass casualty, not just inconvenience. A mistake in design or management doesn't give you a bad quarter. It can wipe out a whole community in hours or days. Is it ethical to encourage people to sign up for that, especially if the plan quietly assumes that some of them will never come back? A one-way mission means a person is committing not just to work far from home, but to die there. And once children are involved, the questions get sharper. A child born on Mars doesn't choose 0.38 G, higher radiation, sealed habitats, or a world where walking outside unprotected is lethal. They inherit it. Their bones and organs might adapt so strongly to Martian conditions that Earth gravity becomes dangerous for them. Are we comfortable creating a group of humans who may never be able to visit their ancestral planet safely? There is also the issue of consent over time. Someone in their 20s might willingly sign up for a high-risk, one-way life on Mars. But what about that same person in their 40s, after a decade of dust storms, hardware failures, crew conflicts, and health issues? There's no easy way to say, "I'm done, send me home." When launch windows are 2 years apart and return vehicles are scarce and expensive, you're locking people into an experiment whose parameters can shift under their feet, while their ability to exit stays tightly constrained. So, you have to be honest about what Mars really is in this picture. It is not a clean escape hatch from Earth's problems. It is not a backup Earth sitting there waiting to be claimed. It is an extraordinarily dangerous laboratory for learning how life, technology, and societies behave on a different world. Treating it as a refuge from climate change, war, or resource crisis here is backwards. If we fail to keep Earth broadly habitable, Mars will not save us. Moving from a warm, damaged Earth to Mars is like walking out of a leaky but heated house in winter and climbing into a broken refrigerator in the garage. You might be able to rig heaters inside the fridge, but you're still in a box fighting the outside environment every second. From a scientific and exploratory point of view, a small, carefully supported human presence on Mars might be worth the cost and risk. We would learn things we simply cannot learn any other way. But calling that a new home for humanity is misleading. It's more honest to call it what it is, a permanent survival experiment on a hostile planet with a price tag so high and a risk profile so sharp that only a tiny number of people will ever experience it directly. So, when you hear the line, "Mars is where we'll go if we ruin Earth," the answer, bluntly, is no. Mars is where a few of us might go to understand how narrow the window for human life really is. For everyone else, and for any serious future for our species, the planet that actually matters is the one we're standing on now. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing content.